Okay, so as always, the lectures will be recorded, posted to YouTube. You should know all of that. Remember, it's the new playlist with 2024. Okay, so don't look at the old one. I've renamed to 2023. Okay, that's the old playlist from the previous Math161 year. Okay, so a quick recap on use substitution with indefinite integrals. Remember, if we have something like this, let's say 3x plus 1 dx, we want to try and integrate this, we would do a use substitution. We see that there's an outer function, that root of something, we've got ourselves an inner function, so we say u is equal to 3x plus 1, du is 3 dx. Okay, we don't have a 3, okay, we've just got the roots of something there, so we take the 3 over. Okay, and with all of this, we can now change the integral to be 1/3 from the du part. Root u, because that's the inside part, is now u du. Okay, and then that was very easy to do, and then you substitute back. Okay, now when we look at definite integrals, we need to continue this procedure as before, but now we also need to worry about the bounds. So let's look at the same integral, but now with some bounds to it. So like, imagine we're finding the area, okay, like we had with last year. Okay, so same integral, but now we're going from 0 to 1. And then we have root 3x plus 1 dx. So we ignore the bounds at first. Okay, we do the normal use substitution as before. So we say u is equal to 3x plus 1. We found our du as normal. Okay, you do any manipulation like we looked at last time. So here we have 1/3 du equals dx. Okay, and before we would put this in and solve. But now look at these bounds here. That lower bound of 0 is not just a 0, it's an x value. So in fact, we can write this as x equals 0 for the bottom, to really emphasize that we're working with x values. And then at the top here, we can put this as, let's put here, x equals 1. Okay, so for these first few, I will write x equals a for the bottom bound, x equals b for the top bound, just to emphasize that those are x values. Now, when we change to this u variable, we can't have x bounds anymore. X was the old one, u is the new one. We can't mix and match between them. So we need to find, given the x bound, what is the corresponding u bound? And that's very easy to do. We've got u equals 3x plus 1. We know how to get back and forth there. So if x is equal to 0, we can write here, if x is equal to 0, then that means u is going to be equal to, what do we get? 1. And then for the other one, we have x is equal to 1. So that means u is equal to 4. So 0, 1, those were the old bounds. 1, 4, those are the new bounds. So when we do the replacement, we need to replace all the x's with the u's like we did. We also need to change the bounds. Okay, so here we can write this as the integral. Now it's going to be u equals 1 to u equals 4, root u, and then we have the 1/3 du from that dx like we had before. Okay, now we just treat this as a normal definite integral like we covered last year. So the 1/3 we can take out. I'm not going to write u equals 1, u equals 4. That's just for emphasis, so you can see here I'll just put 1 and 4. Okay, here we can write this as u to the 1/2 du. And we just go as normal. Okay, we forget the original integral, that's gone. Now we only focus on the new one. Okay, x is gone, it's only u now. Okay, so this is 1/3. Okay, add 1 to the exponents, so that will make it 3 over 2, divide by that, 2/3. And now we have to evaluate this between 1 and 4, just like we did last year. Okay, nothing new here. So we put in 4 and we put in 1. So this will be 1/3. We can times it by the 2/3. So that will be 2/9. We can put the 4 in and we can put the 1. But 1 to something is just 1, so it's like this. And that's it. We get a number at the end because it's a definite integral. We get a definite value. And this is why I said forget about the x integral. Because once we change to u and we substitute the u bounds, we get a number. There's no need to reference the x integral that we had before. That's our answer now. Okay, so the idea, you've got your x integral, convert it into u, you put your u bounds, because now everything is u, you get a number, and that's your answer. Okay, please do not think that you need to go back and look at what the question was. No, that's it. That's our number, the definite value for the definite integral. Okay, any questions on this procedure? Okay, so exactly the same as before. There's just this extra bit here because definite integrals have bounds. Before they were x bounds, now they're u bounds, but everything stays the same. It's exactly what we looked at last year. Okay, let's look at another example. Okay, so here we have the integral from 0 to root pi x cos x squared dx. Okay, so it looks like a normal definite integral that we covered last year, but here we can see it's not like the simple ones from before, because we've got this x in front times cos x squared. Again, we've got that composition there. Whenever you see that composition going on, you need to think u substitution. Okay, not always, but it's a good start because u substitution is the easier of the integration techniques. Okay, later on we'll learn a few more. Okay, so cos of x squared, okay, u substitution with the x squared. Why? Because that's the inner function. That's the go-to. So u equals x squared. As we did before, we need to find du. That's going to be 2x dx. In the original question there was just an x, not a 2x. We take the 2 over to the other side. Okay, so that handles all the inside parts. Now we need to handle the bounds. So let's go back here. And again, if you want to emphasize this, that's fine. We can write this as x equals 0 and x equals root pi. Okay, again, that's just emphasizing that the bounds for this original one are x bounds. And it makes it a bit easier because when we want to find u, we say if x equals 0, what's u? If x equals root pi, what's u? Okay, we can see that clearly here. So if x is equal to 0, then u is equal to, what do we get? 0. And then for the top, if x is equal to root pi, u is equal to pi. Good. And again, let's just put a cloud around this. This is the new stuff that we need to do because of the bounds. Okay, so let's put everything now into the u integral. So we're going to have the integral. The lower bound is going to be a u value, and it will be u equals 0. That's the new lower bound. U equals 0. Okay, and then at the top, the old upper bound was root pi. We did the conversion into u, and we end up with pi. Okay, now cos of x squared, that just becomes cos of u. The dx from before now becomes 1/2 du. Okay, so again, I'll put u equals 0 and u equals pi. That's just emphasis. For the first few, I would like you to write that down, okay, just so you can see which values go where. But later on, as you do more examples, You won't need to do that. You'll see immediately what goes where. Okay, but for the first few, it is easy to mix up what goes where. Okay, so this will be 1/2 the integral from 0 to pi cos of u du. Okay, the integral of cos, or the antiderivative of cos, what's that going to be? Sine. Very good. I'll get to your question now. So we have 1/2 sine of u from 0 to pi. Okay, why sine? Because the derivative of sine is cosine. Remember, you can always go back and forth with the derivative and the antiderivative. Okay, what do we get for the final answer? If you put pi inside, what do we get? 0. If you put 0 inside, you get 0. So we just get 0. Okay, your question?
So we were solving for du, for half du. How did you get dx instead of x dx?
Oh, sorry, that's supposed to be x dx there, yeah. Yeah, I put it correct in the calculation, just on the side here. That should be x dx, yeah. Okay, so then that is for this bit and for that bit there. Okay, thank you. Okay, any questions so far on this? Okay, so everyone's comfortable with the u substitution we did yesterday and this additional bits we're doing now. Everyone's fine with that? Okay, please let me know if you are not comfortable with this, because remember on Monday we have our first assessment with this. Okay, so if you do not understand this, please let me know now before the test on Monday. Okay. Yeah, those that came late, on Monday we have our starts for the tutorials and we're going to have our first tutorial quiz. Okay. Okay, so let's do another example. Okay, we have the integral from 2 to 3, x roots 1 minus x squared. Sorry. Sorry, that was supposed to be 0 to 1. Okay, sorry, the bounds are 0 to 1, not 2 to 3. Okay, so we have this. Again, use substitution. Don't worry about the bounds for now. That comes later. The first bit is to find what should be u, what's our du, and then we can look at the bounds after that. Okay, so don't worry about the x in front. That's not going to help us so much. But we've got the root of something. Okay, again, it's a composition. So root, that's the outside function. 1 minus x squared, that's our inside function. We should let that be u. Okay, and remember what I said last time. There's no fixed rule on what u should be, but there's some idea that you get, given a particular question. Like in that example from yesterday, if we let u be one thing, we did some working, and we let u be something else, the question with the log. Okay, 2 different choices for u, we got the same answer. Okay, so in this case, there's only one choice, but please remember that there might be more than one way to do it. Okay, so if you're looking at my memo and you see me do one way and you do another way, if we get the same answer, you're always fine. Okay, so du, that's going to be minus 2x dx. In the front there, we've got an x. We don't have the minus 2x, so we should take that over to the other side. Okay, and remember to carry down the x. Okay, now that we've done that, that handles the inside part. All we need to do now is worry about the bounds. So let's go back to the bounds here. Remember, this was x is equal to 0 and x is equal to 1. Okay, now those are x bounds. We want u bounds. So when x is equal to 0, what do we get? Okay, so if x is 0, u will be 1. Good. And when x is equal to 1, u will be 0. Good. 0. Okay, so those are the change of bounds. Now we can put everything together to get a new definite integral that's a bit easier to solve. So we're going to have the integral from u equals 1 to u equals 0. Okay, please do not mix them up. U equals 1, that is the new lower bound. U equals 0, that's the new upper bound. So we are going backwards from 1 to 0, but please do not mix them up. Okay, so just because it might seem right to go from 0 to 1 instead of 1 to 0, please do not swap them thinking that it's a mistake. Okay, root of 1 minus x squared, that's going to be root of u. Okay, and then the x dx that was left over, that will be minus 1/2 du. Okay, we can take the half out, and now with the minus, from the minus 1/2, we can swap the bounds. Okay, if you've forgotten your definite integral properties, such that, like having a minus, you can swap the bounds, please go back to your work last year and go over that. You will need to know that. Okay, so the reason I used the minus to swap the bounds is because if I didn't, I'd have a minus and then another minus later. Things can go wrong with too many minus signs. So rather eliminate what you can, just to stop yourself making a mistake later. Okay, so now we have 1/2. Again, the u we can write as u to the 1/2, add 1 to the exponent to make it 3/2, divide by 3/2, that's 2/3, so u to the 3/2, so that's a 2, from 0 to 1. The half and the 2, that can cancel, so we can take the third out. Okay, 1 to the 3/2, that's just going to be 1. 0, if we substitute, that's just 0. So we just get a third. Okay. Everyone okay with that? Okay, good. Okay, so once you get the main idea of what to do, so normal u substitution like we did before, the only thing different is changing the bounds. Okay, so all of these examples is just extra work to do. Okay, in the tutorial there's 10 from what we did yesterday, indefinite, and there's 10 on what we did today. Once you've done all 20, you should be fine with all of this u substitution. Okay, let's have a look at a couple more. Okay, so we have the integral from 1 to 2, 3x over 1 plus 2x squared dx. Okay, something similar to what we did yesterday, but now again we just have the bounds to worry about. Okay, so what do we let u be? Well, we've got that top part 3x, but that's not going to help us so much. So that bottom part we should let be u. Okay, so u equals 1 plus 2x squared. So du, that will be 4x dx. Okay, here we have a 3x dx, not a 4x dx. So let's take this over. Okay, so that handles the top part, and the u definition there handles the bottom part. What about the bounds? So now the new lower bound, if x is 1, u is going to be 3. Good. And the upper bound, if x is 2, u is going to be 9. Good. Okay, and again, those are our new bounds. Okay, please make sure you show the working for your bounds, just so I know what you were doing. Okay, so the new one, so we're going to go from, like we had here, from 3 to 9. Okay, we still have the 3 there, and we've got another constant, a quarter. We can take all of that out, so we end up with 3/4 on the outside. Okay, the du part, that handles the x dx. Okay, so we just have to worry about the u at the bottom. So it's going to be 1 over u du. Okay, so that's going to be 3/4. Antiderivative of 1 over u, that is the natural log. Good. From 3 to 9. Okay, so technically we should put the absolute value because we can't take the natural log of a negative. But notice our bounds are positive, so we don't really need to worry about that. But please just put the absolute value in case. Okay, but if you know that your bounds are positive like this, you don't need to put it, but I'd rather put it there just to be safe. Okay, so here we have 3/4. Natural log of 9 minus the natural log of 3. Okay, now we're not done yet because that 9 and the 3, okay, they're related. 9 we can write as 3 squared. So this will be 3/4, the natural log of 3 squared minus the natural log of 3. Now using our log laws, the 2 in the exponent can come down to the front. So it will be 2 natural log of 3 minus a natural log of 3. So we're left with one of them. So that will be 3/4 the natural log of 3. Okay, so it just helps simplifying as much as possible there. Okay, any questions about this U substitution with definite bounds? Okay, so everyone's comfortable with this. Is there anyone struggling with the homework from yesterday? So everyone was able to do that. Okay, if there's no questions on that, let's just start with the next chapter on integration by parts. Okay, so we're going to cover more of these examples next week. Yeah. The second last line here. Yeah. So here we're using our natural log laws. So the natural log of m to the n, that will be n times the natural log of m. So we took the 2 down, then we got twice that thing minus that thing, so we left with just one of them. Yeah. Yeah, so this was that exponent property from the natural log. Okay, any other questions before we move on? Yep.
So the homework from number 25.
Number 25. Yeah. Yeah, so we looked, I think it was one of the tutorial questions from last year. But whenever we have something like this, so like 1 over 1 plus sine, 1 over 1 plus cos, the trick is to multiply the top and the bottom by 1 minus that thing. Remember when you do your rationalizing the denominator, if you have like 1 plus root 3, you multiply by 1 minus root 3 so that you get that difference of squares. We do the same thing here. So if we have 1 over 1 plus sine x times, and then we put the minus so we get the difference of squares, it will be 1 minus sine x over 1 minus sine x. Okay, so that denominator is as if we factored 2 squares. In this case, 1 minus sine squared can be factored like that. So then this would be 1 minus sine x over 1 minus sine squared. Now we get the difference of squares. 1 minus sine squared is cos squared. So this will be 1 minus sine x over cos squared. Okay, Okay, 1 over cos squared, that's going to be sec squared. Sine over cos, that's going to be tan. And then we've got another 1 over cos, because it's cos squared, so that's going to be sec. And then integrating this, that's easy. We covered those integrals last year. Okay. So this was the only trick that you needed to do here. Okay. Very similar to rationalizing the denominator. Okay. Any other questions about that homework? Okay, I think the rest were very simple, based on what we did. Okay, anything else? Okay, let's have a look at the next section. We're not going to do too much work on it. I'll just introduce it, and then you can have a look at the tutorial 2. That will cover more of the examples to do. Okay, so the next chapter on integration by parts. Okay, just a little bit of warning with this. The problems for integration by parts look very similar to the problems with U substitution. Okay, the reason that is because with integration techniques, there's no fixed rule given a problem. So if I give you an integral, there might be a number of ways of solving it. Okay, so previously I gave you problems that are directly related to U substitution, right? They're like handpicked for that. Now, if I give you a general problem, it might look like a U substitution problem, it might look like an integration by parts problem, but you shouldn't think of it that way. The way you should think of it is, I give you a problem. In your toolbox, you've got a bunch of techniques. Which one is best for that problem? Don't think of it like this one belongs in this group, this one belongs in another group. You're going to get confused with things. Okay, so here we're going to solve this using integration by parts. Maybe you could have used U substitution. Maybe you could have used another technique. Okay, so please don't think, grouped like this and they're all separate. Okay, so integration by parts. So I'll just show you the problem, and then I'll show you why we need this new technique rather than U substitution for everything. Okay, that problem is the integral x sine x dx. It looks very simple. It even looks like something we did with U substitution. If this was x sine x squared, we could have used U substitution. You let u be the x squared, the du handles the x. Here, there's no such thing. If we let u be x, it doesn't help us. We could let u be sine x. Again, it doesn't help us. So it looks like U substitution, quick glance, but it's not. Okay, so we need a new technique. This new technique is called integration by parts. The way it works is whenever we have a product like this, okay, what we're going to do is split it up into two parts. One part we're going to have called U, another part we call V. Okay, there might be different variables if you look at it online, but we're going to stick with the textbook and have U and V. Okay, but just note, other people might use different things, same idea. Okay, so we're going to derive the formula for this. We start off with U, V prime. Okay, so we take U times V, where U is a function of X, V is a function of X. We take the product, and then we take the derivative. Okay, so we're going to start off with the derivative, then we're going to go backwards using an integral, and end up with the formula. Okay, but this is just a quick derivation on how we get that formula. Okay, so this is going to be equal to, we need to use the product rule. So we take the derivative of the first one, leave the second one alone. So it's going to be U prime V plus U V prime. Okay. I hope I haven't lost anyone with the product rule. Okay, now we're going to undo what we just did using an integral. remember, fundamental theorem of calculus, derivatives and integrals, they cancel out. So I'm going to write this a little bit differently, just to emphasize the fundamental theorem of calculus. This first one I'm going to write as d by dx of u times v. This one I'm going to write as du dx times v. And then that last one there I'm going to write as u dv dx. Okay. Now we differentiated. Now right away I'm going to undo what we did with an integral. So I'm going to integrate everything with respect to x. Okay, and then the last one. Okay, so technically that undoes what we did before. We differentiated and then we integrated immediately. Okay, now the integral of a derivative, FTC, that undoes it. So we're back with uv. Okay. Now, these other two, we're not going to undo it right away. I'm going to rewrite it a little bit. Du by dx times dx. We've seen that before. That's just du. Remember, du is du by dx dx. So I'm going to write this as the integral v du. Very similar to this one over here. dv by dx dx. That is dv, like we had with the du part, but now the variable is v. So this is plus the integral u dv. Okay. Now, remember, these are still functions of x, right? It's not like the dv is just dv, right? The v is a function of x. But this is just a nice way of writing it. Okay, now we're going to do a little bit of rearranging. That very last term, we're going to keep this here, and then we're going to take that over to the other side. So we're solving for this, basically. So the integral u dv is equal to uv minus the integral v du. Okay, a little bit of rearranging, but basically we're solving for that last integral there. And this is our formula that we need to know. Please make sure that it is memorized. Okay, so u dv, u is just the function, dv, that's the derivative. uv, those are both the functions. So you see v, we integrated and we got v. On this side, we integrated the dv to get v, and we differentiated the u to get du. The roles swapped. Okay, u becomes du. dv became v. You see how the roles swapped there? Okay, so this is what we mean by integration by parts. We pick a part of the integral to be u, which we differentiate. We pick another part of the integral, whatever's left, to be dv. We integrate. Now, the way it works is if you choose them correctly, okay, there's a number of ways to choose u and dv. There's one way that makes it easy, there's another way that makes it more difficult. Choosing the correct one, that's just practice. Okay, but I'll give you some clues on what to pick. Okay, but the idea is u goes to du. To perform that calculation, you need to differentiate. So it's a good idea to pick u such that it is easy to differentiate. That's rule number one. Rule number two, dv becomes v. We're integrating. We choose v so that it is easy to integrate. Make sense? Okay. So number one, choose u so that it is easy to differentiate. Okay, and what I mean by that is when you differentiate it, It's quite easy to do. It doesn't make it more complicated to work with. Number 2, choose dv. Okay, so you can choose either or first. Once you've chosen one, the leftover is going to be the other. Okay, but you can go either way here. So choose dv so that it is easy. Okay, easy in quotes. It might not be entirely easy, but it's easier than going the other way. Easy to integrate. Okay. Deciding what to pick, that comes with practice. You need to do a lot of examples. You need to try it lots of different ways. And then you build up an intuition on what to pick. Okay, so let's go back to our example here that we said looked difficult. We've got an x and we've got a sine x. One of them has to be u, one of them has to be dv. What will be the best to pick? If we let x be dv, so x dx, we let that be dv, we integrate that. And sine x we differentiate. What would v be in that case? We're integrating x. So, yes? No, if we're integrating x. If we integrate x, what do we get? Half x squared. If we differentiate sine, we get cosine. Okay, so just keep that in mind. So here, if we look at our rule, so v from our choice, that would be half x squared. This would be cosine. Is that any easier to do? Integrating a half x squared cosine x, is that easier or more difficult than what we started with? More difficult, right? Okay, let's try the other choice. If we let u be x and dv be sine x dx, now we're differentiating x. What's the derivative of x? 1. What's the integral of sine? Minus cosine. So now let's see what this integral looks like. So v will be minus cosine and du will just be dx. Is that easier or more difficult? Easier, because now we're just integrating cosine. It's a lot easier than integrating x squared cosine. Make sense? Okay, so what should we do? We pick u to be x and dv will be everything else. Okay, this is what you need to do quickly in your head before you make your pick. You think to yourself, if I do it this way, what do I get? Is it easier? If it's more difficult, you do it the other way. Okay, so with that out of the way, let's do it the correct way. So, u is equal to x. So, you should put it in this like table format. It helps keep track of everything. dv is sine x dx. It's everything else. Okay. Now, that's for the first bit. Now we need to do the swap, right? So we differentiate u, now we integrate v. So what is du going to be? It will be dx, right? Differentiating. Now we integrate. So we integrate. So v will be minus cosine. Good. Okay, so now we did the swap. So u we differentiated, dv we integrated. So now we have all the pieces for this formula over here. So the u and the v, we know what those are now. And the v and the du, we know what those are now. So let's put them in. Okay, so the integral x sine x dx. The first term is u times v. We've got u at the top there, we've got v at the bottom there. So we just multiply them. Minus, please do not forget the minus from the formula. And now we integrate. What are we integrating? V du. There's our v, there's our du. Let's put them together. Okay, so this is going to be minus x cos x. The minus and the minus, let's put that as a plus so we don't make any sign mistakes. Okay, so we started off with a more difficult problem there, x sine x. Now we've reduced our problem to an easy integral. This is much easier to do. Okay, so what is the integral of cos? Sine. Good. So this is going to be minus x cos x plus sine. Remember your pluses and your minuses for that. And then plus c because it's indefinite. Okay, later on we'll do this with definite integrals, but for now indefinite we have our plus c. And that's it. Okay, that's integration by parts. Once you've substituted everything, it just goes back to the normal integration. The only difficult part is choosing what is u and what is dv. Okay, let's have a look at another problem. Okay, so we have the integral x natural log of x dx. Okay. Now we repeat the procedure again. We need to choose something for u, we need to choose something for dv. Keep in mind, u is something that we're going to differentiate. dv is going to be something that we integrate. So let's not make things hard for ourselves and choose something that is easy to differentiate and easy to integrate. So here we need to make our choice u equals something and dv equals something. Okay, let's try it one way. Okay, I already know what the answer is, so I'll start off with the more difficult way. Okay, spoiler. And then we'll see why that's more difficult and why the other one is easy. Let's say u is x, because that seems easy to differentiate, so why not? U is x, dv is the natural log of x. Right, because we think x is easy to differentiate. Let's try that. What happens? The derivative of x is 1. Okay, looks good so far. Now, dv was the natural log of x. What's the integral of the natural log of x? We don't know. Never seen that before. So that doesn't help us. Okay, which means that choice is wrong, right? So you do that quickly. And then we realize, no, it needs to be the other way around. Okay. Remember, there's no fixed rules to this. You need to see what works, and that comes with practice. Okay, so if it's the other way around, then u must be the natural log of x, and dv must be x dx, the leftover part. Okay, while this choice, well, the other one didn't help us, so this must be it. Okay. We've got u and dv, now we need to swap and get du and v. So du. What's the derivative of the natural log? 1 over x. Good. Okay, and then we integrate. V is equal to, integrate that quickly, we get? Good. Okay. For this bit, don't put the plus c. Okay, here we're just finding the thing with c is 0. The plus c comes right at the end. Okay, so don't worry about it over there. Okay, we've got everything we need now. So let's put it into the formula. So the integral x natural log of x dx is equal to, remember what it was? U times v. So let's write that out. Minus. Please remember that there's a minus there in the formula. Minus, and then it's the reverse of what we had at the beginning. So u dv becomes v du. They swap. So v is 1/2 x squared. And du is 1 over x dx. So we put that in. Okay, so again, it looks a bit complicated still. but the x squared and the x, they can cancel a bit, and it becomes very easy to do in the end. So this becomes 1/2 x squared natural log of x minus 1/2 integral. Now we're just left with x, from the x squared at the top and the x at the bottom. Okay, almost done. So this will be 1/2 x squared natural log of x minus, we've done this one already, it's 1/2 x squared. The half and the half become a quarter, so it's going to be 1/4 x squared and plus c. Okay, makes sense? Okay, we choose u such that it is easy to differentiate. We choose dv so that it's easy to integrate. Sometimes you pick the one and then you're stuck with the other. Okay, like in this case, we wanted to pick x, but then integrating the natural log was difficult, so we had to do the other way around. Okay, other times it doesn't matter which one you pick. Okay, so again, it just comes with whatever problem you get. Sometimes it's very obvious, sometimes it's not so obvious. Again, comes with practice. Okay, a few more minutes left. Let's give you some homework, and then we'll call it a day. Okay, couple homework problems. If you're able to solve these, then you've got a pretty good start with integration by parts. Okay, number 2, very standard. For that one, you need to think a little bit about your choice, okay? Because both of them are easy to differentiate and both of them are easy to integrate. So you just need to think about your choice for that. For number 1, same thing, okay? Both are easy to differentiate. Little hint, let u be x squared and dv be the cos, and you'll see that when you get to that next integral, you're going to have to do integration by parts again. So for the first one, you have to do it twice. And then for the third one, you might have to do integration by parts and use substitution. You need both techniques for that. Okay. So a few tricky questions to get you started with this. Okay, any questions? Okay, cool. I'll see you next week.